Welcome everyone to today's talk by Professor Phil Geissler on how nanoscience changes the way chemists think. My name is Laurent Dujambry. I'm the Assistant Dean of College Relations and Development here at the College of Chemistry at Berkeley. And it is my great pleasure to introduce today's talk. Today's talk is part of a new initiative that we call Berkeley Ecosystems, where you can learn, explore, and connect with Berkeley faculty, alumni, students, and industry innovators on relevant topics. This fall, we have two more faculty talks coming up by Peidong Yang on liquid sunlight and Ting Zhu on biodegradable plastics, and two upcoming alumni panel discussions, one on new venture financing next Thursday, and the other on new developments in cancer therapy. We hope you'll register for these upcoming events in the link provided in the chat or later at the ecosystems.berkeley.edu website. Now for a few logistical matters regarding today's talk. Today's talk is being recorded, as were all past events. In the coming days, you will find the recording of today's event and other relevant content hosted at ecosystems.berkeley.edu. We are planning to field a few questions today at the end of the talk, so please use your Q&A function as opposed to the chat function to share any thoughts or pose any questions to Phil, our speaker. And finally, directly following our event, you'll receive a short survey. Please take a moment to provide us feedback on today's discussion, and more importantly, provide some input on future topics that might be of interest to you. And now it is my honor to introduce today's faculty speaker, Professor Phil Geissler. Professor Geissler received his BA from Cornell University and his PhD from the College of Chemistry here at Berkeley. Professor Geissler has served as a fellow at Berkeley, Harvard, and MIT, and is the ongoing recipient of the Packard and Sloan Fellowships. Besides his exceptional research, Professor Geissler is a highly regarded teacher and has been awarded Berkeley's highest teaching award, the UC Berkeley Distinguished Teaching Award in 2011. And if you've ever heard him sing and play the guitar, you would know why he was awarded such a great honor. Professor Geissler is now the Aldo de Benedictis Distinguished Professor of Chemistry at UC Berkeley's College of Chemistry. Please join me in thanking Professor Geissler for speaking to us today. Thank you, Phil.
Thank you, Lo. I'm going to share my screen. All right, all look good.
Great.
Okay, so thank you, Lo. It's a pleasure to spend time with all of you today, if only virtually, and to give you some of my perspectives on the modern field of nanoscience and how it really changes the way we conceive of the molecular world. The title is intended to be provocative, and no matter how long ago you graduated, you know the difference between a phase transition and a chemical reaction. I'm going to try and convince you today that developments in the area of nanoscience can really scramble those things that we think we understand, and in particular, how we understand them as being completely distinct. So I'm going to assume that your notes from Chem 120B are yellowing in a drawer somewhere. And I'm going to start really gentle and develop a broad physical perspective and ultimately transition to some of the specific things that my group has been working on. One of the things you hopefully took away from your studies at Cal is an abiding awe at this regarding Avogadros number. Of course, the value of this number is very familiar to anyone who ever had to solve the ideal gas law 10,000 times, but it's not the specific value that's of interest here. It could be 2 times 10 to the 23rd, and it wouldn't change our lives. The important thing is the enormity of that number. Put things in perspective, there are roughly 1 million seconds in a month. So in 1 million months, there are 1 trillion seconds. That gives you a sense for how big 1 trillion is and why our national debt is so scary. But Avogadro's number is not 1 trillion or 100 trillion or 1 million trillion. It's 1 trillion trillion. It's an absurd number. It's incomprehensibly large. And it's really a statement of scale. It's a statement of the 2 scales that really define chemistry as a science. Of course, we're typically most interested in things at the macroscopic scale of our everyday lives. That's the scale in which they influence us. But as chemists, we appreciate that the properties of those materials, those chemicals, derive ultimately from the molecular scale. And that really is the scale that's bridged by Avogadros number. In a small glass of water, there are Avogadros number of water molecules, which of course are so tiny then that we can't possibly distinguish them by eye. So a chemistry curriculum attempts to really train you to think on both of these scales, the macroscopic and the microscopic. At the microscopic scale, it's really a matter of cultivating imagination because we have no direct experience with that world. But we give you all sorts of tools for thinking about how atoms and molecules are arranged, and perhaps most importantly, how they rearrange. A chemical reaction being the emblematic process of the microscopic world, where bonds are broken and formed. For example, this famous autoionization of a water molecule. Emblematic on the macroscopic scale would be a process like a phase transition. What sense is this very different scale? Of course, a phase transition could be a transition from liquid to gas or liquid to solid. It could be the demixing of oil and water, for example. And in all of those cases, the property that's changing is not a property of one molecule or a small collection of molecules. Liquidness is a property of Avogadros number of molecules. What's surprising about condensing steam is not that it gets denser as the temperature goes down, but that it happens so suddenly at a very specific temperature. Avogadros number of molecules decide to no longer be a gas, but instead to be a liquid, and a feat of groupthink that would be utterly mind-blowing if phase transitions weren't so familiar from our everyday lives. We also teach you in a class like Chem 120B, the theory that connects those two scales, at least in principle, fundamental probability distributions from which in principle we could derive properties of macroscopic systems from their microscopic constituents. That field, statistical mechanics, is the field of my own research, and along with cats and guitar playing, one of my lifelong passions. So what's so fun about this area of theory is that it's not just a mathematical problem. We do have a mathematical framework for connecting these two scales, but it's not something that plays out in a very straightforward way. This is put very succinctly by the famous physicist Phil Anderson, who noted that more is different. The properties of a glass of water derive from a single water molecule, but in order to understand how they do so, I can't think about just one water molecule. And of course, the polarity of these bonds encourages hydrogen bonding. The geometry of this molecule encourages a locally tetrahedral network, a collection of hydrogen bonds networked together. Those things can tile space, and that's the material we call ice. Then once scrambled and disordered, it becomes liquid water. There are many steps in appreciating that connection between the world of a single molecule and a macroscopic material. In a different context, let's consider a solid material, cadmium sulfide, which is comprised of divalent sulfur and cadmium atoms. Again, appreciating the properties of these constituent atoms by themselves, their ionization energies, electron affinities, would never hint to you that these form a highly ordered solid with very interesting electronic properties. The yellow color of cadmium sulfide is not derived from the fact that I drew sulfur atoms in yellow. It derives from the emergent electronic properties of this crystalline lattice. So I'm going to add to this succinct comment, more is different, a statement that seems utterly obvious, and I don't know anyone who is silly enough to put their name on it, so I'll take credit for it, which is to say less is different. So I don't mean this as a trivial reversal of the original comment, but instead to encourage you to think in a slightly different way. Let's imagine we took this little sample of cadmium sulfide powder and just took a single grain from it, a small piece of it. That grain would have the very same macroscopic properties that this entire dish did. And if I were then to scrape off a micron-sized chunk of that, I would again have something that had the same basic physical properties. I could keep doing that, and what I would find is eventually, long before I started dividing this into individual ions, that the physical properties would change. there is a scale between macroscopic and microscopic where things work differently, and that is the nanoscale. So the molecular scale, colloquially, I would characterize as consisting of a few things, a few molecules, a few ions. The macroscopic scale defined by Avogadros number, and somewhere in between, around the scale of a nanometer, is a region that I'll call more than a few, but less than a lot. More than a few in the sense that, that the conspiracy of many atoms and molecules have begun to produce emergent features that would be very difficult to anticipate from the individual constituents themselves. But less than a lot in the sense that the properties are really distinct in very interesting ways from their macroscopic counterparts. So these nanocrystals of cadmium sulfide have very interesting electronic properties. Water, when confined on a nanometer scale between sheets of graphene, can be a very different solvent for chemistry. And so this opens the door to really a new world of materials, a new world of chemistry and solvents that don't behave in the ways that we're accustomed to, with really tremendous practical applications, both in practice now and many more down the road. What's more interesting to me, particularly as a theorist, is not so much the technical capabilities that, that emerge at this nanoscale, but instead what it does to our conception of chemistry, which is founded so intimately on the separation of scales between 1 and Avogadros number. If something isn't large enough to be macroscopic, what does a phase transition mean? It's still something that involves a conspiracy, but not a macroscopic conspiracy of atoms and molecules. If it's a chemical reaction that involves not one atom moving, but a significant collection of atoms moving, how should I think about that? We've left the extremism of our typical perspective of chemistry, and we're really forced to try and re-understand or reimagine that at a length scale that is not a traditional one of chemistry, but is becoming more and more a dominant one in modern research. So I'm going to explore this conceptual challenge at the nanometer scale in the context of a specific phenomenon, one that involves cadmium sulfide nanocrystals. So you're likely, or almost certainly aware that it's possible now through fairly routine solution phase chemistry to prepare nanometer scale excerpts of macroscopic crystalline materials, what we call nanocrystals, consisting of hundreds or thousands of atoms. It looks really easy in a schematic diagram. It's a matter of heating things up a little, injecting the component ions as well as a surfactant. That surfactant plays the important role of keeping these growing crystals from binding to one another and centering, of defining their size. And indeed, what's formed is not just a random aggregate of those ions, but a nicely ordered crystal, as is revealed by high resolution electron micrographs of these systems, like the one shown here. These crystals, while they share the crystalline lattice structure of their macroscopic counterparts, have distinct properties. Perhaps the most famous one is that the color of cadmium sulfide, the color of its photoluminescence, changes distinctly as the size of these nanocrystals changes. This is an iconic picture now of nanoscience, illustrating how the size of these particles from 2 nanometers to 8, this is a closely related material, cadmium selenide, changes dramatically the color of this really brilliant photoluminescence. This is one area of nanoscience that has already really come into the marketplace, and that there are now TVs that are based on precisely that photoluminescence of quantum dots of nanocrystals. And once something's in your TV, it's here to stay. Not only can we make little dots of these by altering the solution conditions and the protocol, we can make them in exotic shapes, for example, rods, as shown in this micrograph down at the bottom. And with suitable encouragement, you can even get those nanometer sized structures to further assemble themselves into larger scale ordered patterns. And panel B here are the very same nanorods, but now they're standing on end and packed in an ordered lattice. This is in essence a crystal of crystals and has yet again a different set of physical properties. But the repertoire of nanocrystals that can be made in this way is not huge. There are many materials that we can use this kind of prescription to make nanometer size excerpts from, but not nearly the full range of materials that we can play with in the solid state on the macroscopic scale. And so anything we can do to expand that repertoire, given this largely unexplored terrain of nanometer size materials, would be a tremendous benefit. So let's just imagine something that we could do that would be really nice. Let's imagine that we could make a nanocrystal out of one material and use it as a template to make a nanocrystal out of a different material. So wouldn't it be cool if we could take a nanocrystal of cadmium sulfide and imagine magically replacing every cadmium ion in the structure with, say, 2 silver ions, still be electrically neutral. And while we're at it, let's be greedy and say we want to do that in a way that doesn't change the nanoparticle's shape or its intrinsic lattice structure. You might imagine how that could happen. You could imagine these cadmium ions in blue here being replaced 1 by 1 or 1 by 2 by the incoming sulfur ions. So firstly, something on the surface could go away and be replaced by 2 silver ions. That could happen around the whole surface. And then to continue that process of exchanging, the interior ions of cadmium would have to migrate their way to the surface, wait their turn, and then exchange. And so a front of that new material, I could imagine progressing into the interior of this nanocrystal until it was a different material, but with the same templated structure that I started with. So that would be really cool. So let me explain to you why that couldn't possibly work. This all has to happen in the context of a highly ordered and relatively stiff solid material. As you might imagine, very dense materials that are also very stiff and highly ordered don't encourage motion of atoms or molecules or ions over substantial scales. You can make measurements and extrapolations that tell you in a material like cadmium sulfide just how rapidly atoms or ions tend to move through the crystalline lattice. And what you find is that at room temperature, that motion is characterized by a diffusion coefficient that is this very, very small number, but it's in macroscopic units. So if you don't play around with diffusion coefficients all the time, you might not know exactly what that's telling us. So let's put that in more concrete terms. If I were to use that diffusion coefficient to ask, how long would I have to wait for a cadmium ion in solid cadmium sulfide to move by diffusive motion over a length scale of just 1 nanometer? These objects are at least 1 nanometer in size. Typically, they are more like 10 nanometers. And the answer is 10 to the 19 seconds. You know how big a second is, and so you know how long that is. Again, if we divide by 10 million to put that into years, you would find that this is now on the order of 10 to the 12 years. And if you go to Google and look up the age of the universe, you'll find that it's actually quite a bit shorter than that. So if I were to actually wait for that diffusive motion to carry these internal ions out of the structure and so that they could exchange with something else, it would take longer than the age of the universe. So this is clearly not something that's going to happen. It's just a nice pipe dream, except that it does happen. And sometimes it happens as simply as immersing one of these nanostructures in a solution that is rich in the incoming ion, in this case, the silver ion. If you just put cadmium sulfide ions in an appropriate solvent with silver ions, go and get coffee, you come back, and quite literally what's happened is that every cadmium ion has been exchanged with a pair of silver ions, and the overall structure and integrity of the crystalline lattice has essentially been preserved. And this is a stark reminder that this nanoscale is really different. It's more than a few, but less than a lot. Moreover, the full pipe dream has essentially been realized in the sense that that the anions hardly moved. This lattice was preserved, and that you can see strikingly in electron micrographs that show you, in the case of a different material, how the incoming material has intruded And you can see the distinction in their lattice structure. You can really map out in an incredible feat of imaging where the ions are and find that in some sense, the anions in the structure basically looked away for a moment and found all of their neighbors had transplanted. So this process is known as cation exchange. It's something that is intrinsic and unique to this nanoscale. And it's not completely clear whether I should think of this as a chemical reaction. If I write it in this form here, it looks very much like a chemical reaction that would send a freshman chemistry student to tables to look up their heats of formation and calculate, for example, whether this should happen spontaneously. It's a chemical reaction in the sense that involves a relatively small number of microscopic constituents moving over scales that aren't that large. This can be done with many different materials. But it's more than a chemical reaction in that it is something that's more than a few. It is something that involves cooperativity, many things acting in concert rather than simple single ions or molecules one by one doing their business as we kind of imagined in the process of exchange, where one by one the ions leave and are replaced. Instead, there's a degree of cooperativity that's more characteristic of a phase transition. Here's some experimental evidence for that kind of cooperativity. These are amazing single molecule measurements where they can monitor the progress of this ion exchange over time for individual nanocrystals. And what they see is that an individual nanocrystal doesn't gradually trade one kind of ion for another. Instead, in this case, this nanocrystal waited around for 20 seconds, not much was happening, and suddenly, in the fraction of a second, its composition changed completely. Right? So this is not a gradual one by one process, but instead something that's highly collective, a sudden change in the nanocrystal's composition. Furthermore, the products of this are not always as simple as a front that's simply progressing into the interior of the nanocrystal. Sometimes that's the case. This is an image showing a core shell structure that has resulted from partial cation exchange. But partial cation exchange can also give much more exotic structures. In the case of these nanorods here, replacing cadmium by copper gives rise to these amazing structures where domains of the new material are now spaced relatively evenly along these nanorods. Again, these are all signs that what's going on here is not simply a sequence of simple transformations, simple chemical transformations, but instead a highly cooperative chemical reaction, something that lies in its nature somewhere between a chemical reaction and a phase transition. So what I want to do is to figure out how this works. I'm not going to be able to answer for you why diffusion apparently is so much faster in these nanoscale objects. That's a very interesting question. I'm simply going to tell you about some efforts to wrap our heads around the kind of cooperativity that's involved in these processes of cation exchange. There is an increasing tendency to assume these days that if you have a problem that involves hundreds or thousands of atoms and molecules, you can just throw it at a computer or throw a computer at it. And by using a combination of molecular dynamics and electronic structure theory to watch the system evolve and actually see a reaction progress. This is a really unfortunate impression because it both grossly overestimates our capabilities computationally for representing and exploring molecular systems, but it also gives a mistaken sense that once you can recapitulate something on a computer, you understand it. That doesn't stop people from trying, and it's kind of interesting to see what happens if you take a representation of a cadmium, in this case, cadmium sulfide nanocrystal, and try to watch its exchange of cadmium by lead ions. This is not even doing electronic structure calculations. This is a really primitive representation of the interactions within this nanocrystal. And even here, we can't get possibly anywhere near the timescale over which cation exchange naturally happens. So even though it doesn't take the age of the universe, it does take many seconds. And to a molecule, that's a long time. When we advance atomistically detailed descriptions of matter, we can do so typically at most for a microsecond. So in this case, they managed to run for 100 nanoseconds or so. And at the kinds of temperatures where cation exchange actually proceeds, you see that very, very little happens. You see some exchange at the boundary here, but no significant progress of that reaction to the interior. They can make something happen by artificially heating the system up. And by the time you get to 600 Kelvin, you see quite a bit of exchange, but you also see that this crystal is becoming significantly more disordered. In some sense, it's beginning to melt. That makes this crystalline environment much more pliable, much more conducive to motion of ions and diffusion, et cetera. But in doing that, I've likely changed the underlying mechanism of this exchange process. And so those trajectories aren't really going to tell me what I want to know. What I want to know is if I waited for a second, not 100 nanoseconds, but a second, what would be the natural dynamics of this transition? So being unable to throw a computer at a problem is actually not a bad place to be. Why is that? Let me make an analogy. One of the many reasons that Cal is better than Stanford is that we're not awash in money. That means that we have to think very carefully about what we spend our money on. In a similar sense here, an inability to take a very detailed representation of a microscopic system and just run it on a computer requires that we think very carefully about what we do represent, how we represent it, and how we can form models with much reduced complexity that might recapitulate the emergent, interesting behavior of interest. I half expected Lo to cut me off here when I suggested that there's some nobility and poverty of the College of Chemistry. So let me keep that from happening by saying that it's good to be a little bit hungry in terms of funding. It's bad to be starving. So it's nice not to be Stanford, but it certainly we could certainly stand to have more help to keep science moving forward at Cal. So this is really my happy space when we have a complicated emergent phenomenon that we simply don't understand, and we face the task of reducing it in complexity to something that we can wrap our heads around. The first stage of this is really a matter of stripping away detail. And in my head, this usually looks something like that, where we've lost the detailed representation of where each ion in this lattice is in detailed three-dimensional space, and instead start to distill this down to features that are generic, ingredients that we know must be there, in addition to details that might also be important, but we can't yet represent. This picture here of turning this ionic lattice into a bunch of red and blue circles is a representation of that process, where I don't literally mean that each of these particles is an atom, but instead a microscopic region over which cation exchange may or may not have proceeded. So you could imagine that each of these blue circles represents a material lead sulfide in a unit cell. Each of the red circles denotes a unit cell of the product material, in this case, cadmium sulfide. So as cation exchange proceeds, I would see the blue circles replaced by red circles. What would I imagine drives or biases the dynamics of that kind of exchange? Particularly in a generic way. This is something that happens with many materials. And so it'd be nice to understand what's common to all of those. And below is a list of things that immediately come to mind. If these are different materials, then likely there is a preference for one material, a unit cell of lead sulfide, to be neighbored by itself or perhaps by the other material. For the systems that we're thinking about, a material would probably prefer to be next to itself. So there's a local chemical preference that emerges from the ionic properties and the nature of bonding between these constituent ions. But it's a generic component of an exchange process that is local microscopically. It's really something that has to do with a unit cell and its immediate neighbors. And again, very generic. Of course, these objects that we're talking about carry charge, the ions carry charge. And so I might worry about interactions that are longer in range, that extend beyond a lattice spacing here. that are electrostatic in nature. I might also recognize that, as I've drawn here, different materials have different size. The unit cells have different size. Lead ions are bigger than cadmium ions. That too has a generic consequence that must be a part of cation exchange. Simply put, if I were to take one of these large unit cells of lead sulfide and stick it inside a lattice of cadmium sulfide, I would have to make room for it. I would have to locally distort the lattice. The same thing would be true in reverse. If I took one of these small things and put it inside here, the lattice would contract around it. And there's an elastic cost to doing so. Distorting structured materials always involves costs of this sort. And this is something that we expect to be a very generic feature of cation exchange. At this level of representation, you could imagine including other more exotic and complicated things like I've listed here, but I'm going to stop the list there today and tell you about what happens if you focus on perhaps the two simplest of these biases, just local chemical preferences of one material to be neighbored by itself or by a different material, and this mechanical cost of putting big things inside a crystal with a small lattice spacing, or vice versa. The process of the kind of theoretical work that my group does then proceeds to construct a microscopic model based on that perspective to then solve that model through some combination of formal analysis and computer simulation. I'm not going to drag you through almost any of that, but instead just give you a sense of how these models are constructed very roughly and the kinds of things that we learn from them. So firstly, to describe this local chemical bias, the simplest thing we can do is exactly what we do. We assign an energy to neighboring pairs of these particles. I'm going to call them particles or atoms, even though they represent something like a unit cell. I'll say that when A is next to A, and A is the blue thing, there's some energy associated with that, which I've denoted there. When B is next to B, there's a different energy. And when A is next to B, there's a different energy still. In essence, what I've done here is to just penalize the mixing of these two materials, provided that each material prefers to be next to itself. Now, if you took Chem 120 relatively recently, you might recognize this kind of simplified description as precisely the way that we describe macroscopic phase transitions, conventional transitions like the boiling of a liquid or the separation of oil and water. And so you know what the phase behavior is as a consequence of those kinds of interactions. So let's imagine a phase diagram in the plane of temperature and composition. So C equals 0 here means all red, all of the product material, whereas C equals 1 denotes all blue, all of the initial material. And as you know, for something like boiling a liquid or oil separating from water, there's a critical temperature above which there is no phase transition. And below that, there's a range of concentration where I get not just one phase, but two phases coexisting, like a glass of water with a lid on it exhibits coexistence between liquid water and water vapor. So that's the characteristic phase behavior, phase diagram that I know is going to come out of this local preference as described in this simple way. We're going to take a similarly simple approach to describing the elastic cost of mixing these materials. I'll simply say that, that each pair of neighboring atoms has a preferred length of separation dictated by its size. So in this case, the red guys have a small preferred length, the blue ones have a large preferred length, and the mixed case prefers a length somewhere in between. And I'll assign the simplest energetic penalty I could to distorting any of those bonds away from their naturally preferred length, which is in essence a harmonic oscillator, to make an energy that increases quadratically with the size of that local deformation. Now I want to emphasize that the ingredients of this model are really simple. They're as simple as I described. Writing them down in mathematical equations makes them look a little bit uglier, but in their essence, they're no more complicated than what I just said. But that doesn't mean that I'm positing a very, very simple mechanism for this process of cation exchange as a whole. This comes back to the notion that more is different. Even very simple ingredients of a model involving many interacting particles can give rise to very surprising and sometimes exotic emergent behavior. So what do I expect from this elastic bias? We said we know precisely what to expect from the local chemical preference by analogy with boiling a liquid. So let's ask here. Well, the lowest elastic energy I could possibly have would be not distorting any of these bonds away from their preferred length. And that's only possible in the pure materials. If I have all A, which is blue, or all B, which is red. In this case, every single pair of neighbors can adopt its preferred bond length, and there's no cost of elastic distortion. Once I start mixing them, I necessarily have to introduce distortions. And so there is an energetic penalty to mixing. And that is the essence of this elastic bias, is penalizing mixing. But we just said that we already had a description that did that. Just considering these local chemical biases, we already had something that penalizes, that discourages mixing. So have we just added in something redundant? Are we just going to end up with the same kind of phase behavior we would expect for a liquid boiling? So we've developed theory to answer that question, but it's more fun to look at computer simulations. So I'm going to show you some trajectories from a Monte Carlo simulation of the model that I described to you at a variety of different conditions to explore its phase behavior, whether it behaves in the way that a liquid does when it boils. So I'm going to consider a few different points in the phase diagram and just see what the system looks like. Okay, so I'm going to start here. If this were an analogy to boiling a liquid, I would expect to see both phases present, a blue-rich phase and a red-rich phase, and an interface separating the two of them. So let's see if that's what happens in this elastic model. And the answer is no. These two things seem to be mixed and not to have a desire to phase separate from one another, as we would expect for coexistence of liquid and vapor. So maybe we're just in the wrong part of the phase diagram. So let's move over here to a composition that has more blue particles and fewer red particles and see what happens there. And now we find curiously that the red things don't even seem to want to stick to each other. Even though macroscopically these materials want to be separated in the sense that the lowest energy state would be a pure material, there doesn't seem to be any tendency for these things to aggregate, which is really curious. So now let's go to a lower temperature and let's try and help it out by starting with a phase separated state and see what happens. And as time progresses, we find not only do these materials mix, but they mix in an intimate and a spatially ordered way. So we've discovered here the existence of modulated order, an exotic phase behavior that emerged from a very simple description of generic features of materials that are mixed in the way that, that nanocrystals must be mixed in the process of cation exchange. Right, we can map out these phase diagrams in quite a bit of detail using both theory and simulation. And that's something we've done in 2 dimensions. I showed you results in 2 dimensions because they're easy to look at, but very similar behavior in 3 dimensions, where again, these modulated phases emerge. So we have this interesting conundrum that elastic biases favor pure materials that are unmixed. But once I force them to have an intermediate composition, what they do is not to separate, but instead to mix in this highly ordered fashion. So what are the consequences then for this process of cation exchange? Firstly, I need to note that the results that I've shown you so far, those movies and those phase diagrams, pertain to macroscopic systems. Even though these little simulations I'm showing you involve just on the order of 100 atoms, we've used a trick here. The trick is to take this part of the system and repeat it periodically above and below, left and right, to give it the impression that it's surrounded by a bulk environment. Here I'm considering instead a nanoparticle, something that doesn't have this continuation, and something that has then free boundaries in a way that this macroscopic system simulation did not. And what we find is that when we introduce free boundaries, we find that these materials don't mix. that those interesting exotic phases that I was just showing you aren't present at equilibrium, which at first was kind of sad because we were excited we had discovered these generic exotic modulated order phases. And now they seem not to be pertinent on the nanoscale because the boundary conditions are different. But if we look in detail, we can calculate effective interactions among these red and blue particles and get a sense for whether a blue thing likes to be surrounded by red or by blue as a consequence of all these elastic interactions. This effective potential still has a very interesting spatial structure to it, highly reminiscent of what we saw in the macroscopic case, even in a nanocrystal. Near the surface, things are different, but dense in the interior, we see some tendency, some favorability of that mixed modulated structure. And so it's then an interesting question whether that phase, that structure, rears its head in the course of a process like cation exchange. So let's explore exactly that. What I've shown you previously were computer simulation results that were intended to survey the equilibrium distribution of structures, and not so much the dynamics. So what I'm going to show you now are a different set of computer simulations that are designed specifically to examine the dynamics of this exchange process through individual moves that involve at the surface of a nanoparticle exchanging red for blue, one material for another, or in the interior of a crystal swapping to adjacent things as if ions were moving past one another through the material. All right, let's get grounded first by considering a case that doesn't have any energetic biases. There's no preference at all here for red to be next to blue or vice versa. This I'll call the non-interacting case, really just for reference. We start with blue and red first comes in from the boundaries. And because of randomness, we see patterns here that are pretty, but are random. There's no sense or order to these things. Let's next move to the model that I said was equivalent to a liquid boiling, a conventional phase transition, the so-called Ising model. This is just describing the local chemical preferences of each of these materials to be next to itself or to be next to the other material. And now we see a very different character of exchange. We see that exchange proceeds fairly rapidly over the first few layers and then halts. What's happened is that it's formed neat interfaces between domains that are red and blue, much like a system at phase coexistence, that are then very, very slow to advance because it involves deforming that interface between them. So this is a case that is kinetically not at all conducive to exchange beyond just the shell of this material. It hardly penetrates much into the core. And indeed, we've seen experimental results that look just like that. But now let's look at the elastic case. Okay, so I'm just including those simple mechanical interactions that tell me big things next to big things have a large preferred bond length, and little things next to little things have a smaller preferred bond length. What do we expect? If this proceeded at equilibrium, then we would see a small domain of the incoming material simply grow until it encompassed half of this and then 3/4 and then swept over the entire thing. What we see is instead these exotic modulated order phases rearing their head. Even though these aren't stable at equilibrium, they play a large role in the dynamics of exchange. You can see that exchange here is much more facile, even though there is a front proceeding through this. This effective encouragement of mixing on microscopic scales that comes from those elastic interactions actually really promotes the advancement of that front to proceed much more rapidly than I would expect if I only had these local chemical preferences. All right. We see very similar behavior in 3 dimensions. For nanocubes, you can see as this thing proceeds, again, the emergence of this modulated structure and these exotic structures transiently as exchange proceeds. There's also very interesting shape dependence. This was a little movie of a nanorod at intermediate composition. And now a consequence of those elastic interactions has been to form a natural spacing that you might be able to detect with your eyes here between domains that are rich in one material or the other, and very much akin to what's been observed in experiments. So that's most of what that's really all of what I wanted to tell you about today. In summary, the main thing I wanted to communicate is how interesting this scale is of more than a few, but less than a lot, not just in introducing new kinds of materials with new properties, but really in challenging the ways that we think about transformations, which we tend towards from our training, tend to think either macroscopically or microscopically, not in this intermediate scale. As for next steps, we clearly have done little justice to the chemical reaction aspect of cation exchange here because we've stripped away so many details, and that really is the next step of this line of research, is to add in some of that realism. And there are many challenges that face that. I'll drop the word machine learning as one of the techniques that we intend to leverage in doing this. But to really fully explore the nature of this process that is somehow neither a phase transition macroscopically nor a simple chemical reaction microscopically, but instead somewhere in between. So let me finish by thanking graduate student Lane Frechette, who is, of course, a Berkeley alum who graduated just a couple years ago, and a close collaborator from the University of Vienna, Christoph Delago. I will also thank the De Benedictis family for sponsoring the chair that I hold, and some institutions that helped fund this work. And finally, to thank you, and I would be very happy to take some questions.
Oh, that's wonderful, Phil. And yes, thank you for the plug that, of course, all great science and scientists need financial support, of course. I'm going to start with a question that came in the Q&A kind of early on. So molecular is at a smaller scale than nano, which is at a smaller scale than nanocrystal, which is at a smaller scale than macro. So in theory, might there be a larger scale beyond macro at which the chemicals under consideration behave in a different manner?
So for the materials that we play around with, the answer is that it's not likely, and the reason is this: there's a way you know that you've hit the large system size limit, and that's when a system behaves as if it were made of many parts that are uncorrelated with one another. And that really is an essential component of the mathematical structure of thermodynamics, that a macroscopic glass of water I can really regard as being a collection of small regions that are themselves consisting of a large number of molecules, but essentially don't talk to each other. There are no real correlations. And once you've hit that limit, you can keep making the system bigger, and you really don't expect anything more exotic to come out of that. Are there materials where you don't hit that limit? If you have a material that carries a net charge, an extensive net charge, that's one case where you don't hit that limit of being able to break something into non-interacting or uncorrelated constituent parts. But macroscopic systems that have a net charge don't happen. They don't happen because they would be enormously explosive. So I should never rule out the possibility of anything, but I'll simply say that we have very good reason to think that the macroscopic limit really is a limit of large scale.
That's great. And I'm going to field one more question from the Q&A, and then we have a surprise live question for you, Phil, from one of your colleagues.
Great.
And let me see if I can get this question right. In many of your later simulations, you had infiltration from the outside. Are there particular surface area to volume ratios or circumference to area for 2D, either upper or lower limits beyond which you see a change to other behaviors?
So it's a very interesting question. And I guess what I would point to most directly is the strong shape dependence that we've seen in this example of cubes versus rods. So this is an indication that these things are very sensitive to geometry. From what we've seen, if you keep the geometry fixed, if you fix the aspect ratio and you just make this thing bigger or smaller, the dynamics that I described don't change in a really qualitative sense. But if you start changing the aspect ratio, changing the shape, then you can see really new behavior emerge. It's also worth mentioning that we've treated these surfaces as if they're all equivalent, that exchange happens equivalently at each surface. One of the interesting features of real nanomaterials is that different surfaces are quite different from one another, both because they represent different facets of the crystal and because they are passivated differently by the ligands that inevitably form a coat around these crystals. So all of those things together say that, yes, that's a very good question of thinking about the sensitivity of distinct surfaces and the relative size of distinct surfaces can give rise to very different behaviors here.
Well, let me do this. We're going to attempt to take a live question, Phil. We never know how technology will behave. But actually, your colleague, Professor Alex Pines, has listened in today and has a question for you. Alex, could you unmute yourself? And
yeah, I think I've unmuted. Questions, can you hear me?
I can hear you just fine.
Great, Phil. So let me start by saying, not just great lecture, but fantastic lecture, as always.
Thank you, Alex.
One is a comment, one is a question. Let me start with the question. The question is, did you consider, and my feeling is this maybe not unrelated to the issue of the elasticity of the different sizes, the question of defects, because in stiff crystals, even the most famous case that I worked on 40 years ago is stiff ice at very low temperature. There's an equilibrium concentration, there's a residual entropy due to Bjerrum faults. Those are cooperative in nature, and as stiff as it may be, they move very quickly. And the famous case is injecting hydrogen fluoride on the surface of ice, and it very quickly moves through the crystal. So there could be something different about the defect possibilities in the nanocrystal versus the macroscopic system.
Absolutely, and this is the sort of thing that we will definitely be looking towards as we consider more realistic descriptions of these materials. I think there probably are amendments of this kind of description that describe precisely the kinds of defects that you're describing here. I will say that this doesn't provide us an easy out for rationalizing the time scale of exchange relative to macroscopic expectations, and the reason is we know that these lattices and nanocrystals aren't super rich in defects, because we can see in high resolution TEM that they are significantly ordered. If a nanocrystal contained just a couple of defects in the process of exchange, they would be purified very quickly. Even in bulk, the equilibrium concentration of defects for these kinds of materials would be extraordinarily small in number in an object of this size. That certainly doesn't rule out different kinds of defects emerging at the scale because of the influence of the surface, for example. And that's precisely the kind of thing that we're going to be looking towards moving forwards. That's a great question.
So Phil, let me take this one first.
But I want to hear Alex's comment. I thought the comment was coming second.
Alex, are you still on? Maybe it's not, Phil.
Okay. All right.
We'll save that one for the faculty club for you too.
All right.
Will do.
The example you showed was from solid to liquid reaction, solid-liquid reaction, nanocube in solution. Will we see a different aggregation behavior in solid gas ion exchange?
That's an interesting question. Okay, so if I understand the question, here I've imagined, at least so in the experiment itself, this is all happening in solution conditions such that the incoming material are solutes in a solution that invade this thing. In the descriptions I've shown here, there is no representation of the surroundings except as a reservoir of material that can come in. So an interesting question then is what you would see if you did this not in solution, but instead in vacuum, in essence, well, in vacuum, while sputtering in the incoming material. Firstly, I'll say that it's probably going to be somewhat difficult. One of the common strong driving forces for cation exchange is choosing a solvent that is much more friendly to one of these species than another. And if you get rid of the solvent, that's kind of hard to do. But it certainly could happen. I'm not aware of nanocrystal ion exchange that's been done in that kind of environment. That doesn't mean it hasn't been done. It's just not something I'm aware of. It's an interesting question.
And I'm going to end with this last question. First of all, there was a number of people that have said great talk and thanks for the insights. I'm curious, this person says, I'm curious about how much shape is dependent to kinetics. For example, compare between Q dots and 1D nanorods, or just imagine about super lattice structure that consists of nanomaterials. I'm curious about how much it affects, I guess, the structures, the states.
So I'm imagining that question might have come in before I got to this part of the talk. It really is anticipating precisely what I showed here, which is fantastic. That these are very sensitive to geometry, and that simply emphasizes a theme that is endemic in the world of nanoscience, which is for small objects, surfaces matter a lot more than they do for large objects, and that has, as a consequence, often a dependence on geometry that is much more sensitive than we expect at very large scales. And here is simply an example of this. This really is a very similar kind of process occurring in a cube versus a rod. And whereas here we see structure that's modulated on the order of a couple lattice spacings, and here we see stripes that extend periodically through the rod. So absolutely, this is a big theme in nanoscience, that shape matters, and we see that very much here in the kinetics.
Well, thank you to all of those that have joined us today. We had a great attendance of over 90 folks coming on live, and I'm sure others will access your talk recording. And thank you, Professor Geissler, for sharing just a sliver of your deep knowledge and passion of chemistry with us today. We hope you'll join us for future Berkeley Ecosystems events, and you can always view past events and other content at ecosystems.berkeley.edu. As a quick reminder, please take 2 minutes to complete our post-event survey to provide us feedback. And we hope to see you again soon. And until then, as we say in Berkeley, go Bears.
Go Bears.